Hi everybody, this is Mr. Schaefer, and I have for you today a calculus lesson on how to calculate the rate of change of functions using a variety of techniques, and we're going to see that in a few examples in this video today. So a reminder that there are 4 approaches that we're going to use in this course to study calculus, and they're listed up here in the corner: numerical, graphical, algebraic, and verbal. And if you look at this note sheet, you're going to actually see examples of these different kinds of problems. The first one here I know is a numerical problem because there's simply a table of data that's here in front of me. There's no picture, there's no function that's given, so I'm going to actually have to apply my calculus to just these numbers that I'm given. In problem 2, we see that there's a graph that's given. So I would call this a graphical approach. We're going to use some kind of graphical approach to find the rate of change in problem 2. On the back of this worksheet, number 3, no pictures given, there's no data table, but I do have a function. And so that would be an algebraic or more of an analytical approach. And then the final approach is a verbal one. So anytime a question on a free response quiz or test or assessment asks you to explain something, you're going to justify or show or prove or verify, that's going to be where you're going to see that verbal component of calculus come into play. So diving in here to number 1, it says a pebble is stuck in the tread of a car tire. So here's this little car tire that's spinning. The pebble is that dot. As the wheel turns, the distance in inches between the pebble and the road is going to kind of vary. And what we have here in this chart is how the distance between pebble and road are varying. And the question here says to find how fast y is changing. So that's an average rate of change question when time equals 1.4 seconds. So what we're going to use is what's called a symmetric difference quotient. Remember that rate of change can be found by f of b minus f of a all over b minus a. So I'm going to find in the table here where 1.4 seconds is. I'm going to bound that using the 1.3 and the 1.5. So it's really these entries that I want to use in my difference quotient. So f of 1.5 minus f of 1.3 all divided by 1.5 minus 1.3. And the data here in the table is going to be, looks like 0.34 minus 0.54. And again, divided by 1.5 minus 1.3. So compute that. You can use your calculator, or just very quickly, we can get, looks like negative 0.2 divided by 0.2, so negative 1 inches per second. Check units carefully. We're dealing with inches in the numerator, a change in inches divided by a change in time. So the units at the end would be that inches divided by seconds. So negative 1 inches per second. I'll skip 1.7 for now and jump to the 2.0 seconds. What's weird about this is I can't really bound the 2.0 with a symmetric quotient. There is no 2.1 data point that's there for me to use. So the best that I can do is just go 1.9 and actually use the 2.0 itself, since that's a data point that I know. I can't go and invent numbers off of my data table. I'm only allowed to use the numbers that I see. So for this one, find the average rate, f of 2 minus f of 1.9 divided by 2 minus 1.9. And that, again, from the table, would be 0.37 minus 0.24 divided by my 2 minus 1.9. So approximately 1.3 inches per second would be the rate of change at 2 seconds. And again, these are all approximations. I have nothing very exact or precise here, and it's okay to have an estimation in these problems. But I do want to make sure I understand what the units are telling me. my approximation for how fast the distance between the pebble and the road is changing at time 2 would be about 1.3 inches per second. Notice also the fact that I have a negative sign up here and a positive sign below. So that should also tell me something about what's happening to the distance. The distance between the pebble and the road is decreasing in my first case, but then at 2 seconds, the distance between pebble and road is increasing. Again, because of the sign, SIGN, the sign that's on those numbers. So here's a graphical approach, and I have this one filled out for you already. I'll just kind of talk about what I did. Remember that the rate of change is the secant line between 2 points, but if I'm looking for an instantaneous rate of change, that's essentially the tangent line. So what I did is I took a ruler and I actually sketched 3 tangent lines that correspond to the 3 given points here, 1 second, 3.5 seconds, and then 7 seconds. You can see those 3 tangent lines. And what I'm doing is I'm just doing a little kind of mental delta y over delta x. I'm trying to figure out what is that slope. Rise over run, approximately 10 divided by 0.5 for an increase, a positive slope of 20 feet per second. That's an approximation. You might do it and get something like 22 feet per second, or maybe you get 15 or 18 feet per second. And that's okay. We're just approximating with these tangent lines, maybe with a ruler and a pencil. Nothing really exact or precise here. But I do want to have a positive value. It's clearly increasing at time 1 second. At time 3.5 seconds, it looks like I'm exactly at the vertex here of this quadratic function. So I put a level horizontal tangent line, and that line has a slope of 0. So I would say that the instantaneous rate of change of the soccer ball here is 0 feet per second in its velocity. And then finally, as that ball comes back down, time 7 seconds, again, just sketching a tangent line with my ruler, I'm approximating a delta y over delta x. Notice I'm falling down, so a negative y value, a negative change in y, and then a small positive change in x. So I said about negative 15 divided by 0.5 for an overall instantaneous rate of change of negative 30 feet per second. So a negative velocity right there on that ball. But the slope of the tangent lines along that function kind of are telling me approximately what those instantaneous rates might be for the problem. So that's how you would maybe do a graphical approach to a rate of change. And that brings us to this last example, and it's the most complex. It's asking quite a bit here, and it's an algebraic approach. We're given a function, which is right here. Bacteria in a laboratory culture are multiplying. They're increasing such that the surface area of this culture in square millimeters, notice the units, is given by that function, and t is in hours since the culture was started. So letter A says to graph this function on your calculator and find a suitable window. How would you describe the rate of change of A as t increases? So if you have your calculator, go ahead and graph that function in your TI-84s. So here's y1, 200 times 1.2 to the power of x, power of t. And the window that I found that worked pretty well was to maybe go with, let's try negative 100 for y min, and then positive 400 for y max. You can go by hundreds, I guess, for that y scale, and then let's hit graph and kind of see if that works. So there's the picture. This is an exponential function. And the question says, as time passes, as time increases, what is going on? How would you describe the rate of change in this function as that happens? And to maybe illustrate this better, I'm going to show you Desmos. So if you are able to look at a computer, Desmos.com has its own really nice dynamic graphing calculator feature and so forth. And what I'd like you to do is to click on these 3 horizontal bars where it says Open Graph, and there's a series of sort of pre-built Desmos mathematical analysis graphing systems that you could pull up here. And the one at the very bottom here, actually there's a couple at the bottom here that all say calculus. And the one that I'm going to look for is the one that says tangent line. So if you want to click on that and click Open Graph, it's going to create for you a way for you to type in a function into Desmos along with a tangent line that's right there on top of the function itself. Now the default is the sine function. I don't want that though. I want to type in our exponential function. So way up here in the corner, let's delete it and type in 200 times 1.2 to the power of t, or I guess in this case it's x. And the window, to adjust windows and decimals, there's a little wrench button here in the upper right-hand corner of the graph. It's called Graph Settings. I'm going to click that. And down here, I have an x min, x max. And then on the y-axis, a y min and a y max. So on the y-axis, I'm just going to fix that to negative 100. And I'll try to go positive 400 again. And that should be a nice window for me to see my picture. So that's how you can pretty much type in your function and analyze what's going on here with this situation. Now, what I would propose is take a look at, you can actually click this point and kind of move it around. I turned my tangent line into a dashed line just to make it easier to see. But if I go here on the far left, and I can even click this play button and watch the animation of that tangent line going up the function. There we go. Pull it back here. As time increases, what we see is the slope of that tangent line. Here it's positive, but it's not, it's relatively small. But then as you go forward in time, we see that tangent line increase more dramatically, and so forth. So what I might say on my paper here to answer this question, as t increases, the rate of change of a of t, and that's like saying the slope of a of t, increases. So there would be a way to kind of describe what happens to that function. Now, letter B, what is the average rate of change of increase in the bacteria from 2 to 2.1 seconds? And then what are the units? So first of all, typo right here. It should not be seconds. I believe the time was given in hours when we fix that up first. All right, so I want to figure out a rate of change calculation. We're going to use the difference quotient from 2.1 to 2, or 2 to 2.1. And on the calculators, there's a really nice feature again. If you pull up if you hit alpha y equals, you can get the numerator denominator feature. And then alpha trace is where you can retrieve your function. So if you have your function typed in y1, and I want to know what is a of 6, I can just hit enter and type in a of 6 or f of 6, and then just hit enter, and I'm good to go. But up here is the difference quotient that we're looking for, and I have a value of 52.990. Let's check the units right there. Square millimeters is the change in the numerator there. And then a small change in time, so divided by hours. And then what does that mean? Well, verbally, and by the way, whenever we see questions like this, that's a verbal approach. So here's my explanation. What does this mean? Down below, there's the word explain. From 2 to 2.1 hours, the surface area of the bacteria culture increases by 52.990 square millimeters per hour. Letter C, write an equation for R of t, which is the average rate of change from 2 to t. So average rate is this formula. But from 2 to t, this is like my a value, and the t is my b value. So that would be, we'll go a of t minus a of 2 divided by t minus 2. I'm just sticking a variable in there for the second point. And explain why r is undefined at time 2. Well, if you plug in a 2 right here to r of t, then I'll have a 0 over 0, and I'll have an undefined indeterminate form, division by 0, so it's going to be an undefined expression. There is no value, no answer, so I can never be right on, exactly on a number. So that's why for part D, to conclude this problem, I can't get the instantaneous rate of change directly at 2, so I've got to get creative and move a little bit off of 2. So to close out this problem, why don't we go to 2 point, actually I'll go pretty close. So how about a of 2.001 minus a of 2 divided by 2.001 . There we go, 2.001 minus 2. And if I compute that on the calculator, I should get about 52.513 square millimeters per hour. And then what I might say is, to this question, what does this mean? I'll type out a solution. Let's be really specific here. At t equals 2 hours, the surface area of the culture is increasing at the rate of 52.513 millimeters squared per hour. Notice how I mentioned the time. Time equals 2. I'm talking about what is increasing. I'm not saying it is increasing. I'm saying the surface area of the culture is increasing. Really specific. Try to avoid pronouns in calculus. And then lastly, how do we find a more accurate estimate of this instantaneous rate? Well, let's just get closer to the number 2. Instead of 2.001, what if we went to 2.000001 and then computed that average rate difference quotient? That would get me a number that is even closer and better. And so what I might suggest here is let delta t approach 0. And that's this idea of a limit. Choose a value closer to time equals 2 hours. And then do that difference quotient one more time. And by the way, if I go back to my Desmos graph, and if I pull this point to go right at 2, let's take a look here. I want the a value to be exactly 2. So there it is. I'll turn on that ordered pair. So that ordered pair is 2, 288. And then down here, I have a little extra cell where I typed in g of a. G of a, according to the way this is all laid out, is actually the precise numerical slope of that tangent line. And if you notice, the slope here is 52.508. So really, really close to what we were approximating here earlier, 52.5, 52.9. But the exact answer, or the really, really, really close answer here, is 52.508. So those are all examples on how we can find rate of change of problems in calculus. And that's what the instantaneous rate of change of functions is all about.